Okay. Hi, this is lecture number 2 of the Lectures in Metamathematics series. So I did give this lecture a few times, twice actually, for the 2 different sessions, but I messed up both times, and I messed up bad enough that I'm just going to redo the whole thing because I made things really confusing and I feel really bad about it. So with me is Lisa. Please say hello.
Hi.
Lisa's here. She knows quite a bit about logic already, but she's here to, she hasn't seen the lecture yet, so she's gonna be like asking questions if she has questions. And then also keep me company so I don't go insane, because I love her very much. Okay.
I love you too.
Okay. Did you get to finish the first lecture?
No.
Okay. Well, basically, right now I'm starting with, like, at the end of this lecture, we define what a model is. So propositional calculus, I included the truth tables for people who weren't really familiar with, like, the actual definitions of the connectives.
I went through the truth table last time, yeah.
Yeah. So after propositional calculus, we still need ways to refer to objects and refer to objects specifically in structures. So I'm going to throw in kind of just a bunch of new definitions and then some more definitions, and then they will all fit together. So first, we're going to use lowercase a, b, and c to just denote constants. Constants are just individual objects. Unlike variables, which are, variables. They vary over a set. I feel like when I first learned about this, I was really confused about constants. It's literally just like putting a pin in a specific object and saying, this one. And we use A, B, and C to denote this abstractly. Quantifiers. For all there exist. This is not new. Functions and relations. So arity of a function is how many arguments a function takes. So addition is binary, takes 2 arguments. A unary unary takes 1 argument. Binary takes 2. Yada 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 yada. And you can just imagine n-ary functions. That's how we say n-ary, as like, this is a function that takes n arguments. And relations, which are also n-ary. So we use like capital R, P, and Q to denote relations abstractly, but the relations that you're used to are like equality, less than. It'd be really great if my pen would work. Is contained in. And in the beginning, we'll be working a lot with binary relations. So for now, just relations between.
Could you read the difference between functions and relations?
So a relation, a binary relation could ask, are X and Y equal? So this will have like a truth value as an output, or it won't even have an output. It just says, I take in X and Y and I compare them with this relation. Whereas a function actually does something to both of them and has an output. Whereas a relation is just an atomic formula, which we'll get into momentarily. It's just a statement. Okay. A relation, it's a relationship. It's a relationship between things. Okay, now that we have all these new ways to denote specific objects, we can actually start building up like logical statements and start asking logical questions. So we need to define terms, atomic formula, and a formula. So when I say inductive definition, I mean terms. These are like the smallest logical objects. And then you can use terms to build up atomic formulas, and then atomic formulas to build up formulae, whatever. So first, terms. Oops. Wow. Thanks, Johannes. I don't know if Lisa, could you hear that? Mm-hmm. Okay, awesome. Terms are constants, variables, and output of functions. So whenever f is a function, an n-ary function, if I put in n terms, all of these are terms, what I will get out will also be a term. So again, terms, the smallest things. Atomic formula. If R is an n-ary relation, then if we put in n terms, what we get out is also a term. So it might be a little confusing because I'm not saying that a relation has an output. I'm just saying that this object itself is a term. Mm-hmm. So example, this one, x does not equal to y does not equal to z. So I'm actually, instead of phi, I'm gonna write r, so it's clear that I'm talking about a relation. And the relation here is inequality. Mm-hmm. So these here then are terms. Mm-hmm. Okay. Or no, our atomic formula. So atomic formulas, second smallest thing, built up from terms. Now for formula. Every atomic formula is a formula. And then we can put together, so when I say inductive definition, I mean, assume you start with two formulas. Given any two formulas, you can create new formulas with the connectives. Okay. So if phi is a formula, then not phi is a formula. If these are both formulas, then so is phi and psi, phi or psi, phi implies, phi is equivalent to. Cool. These are all formulas. And of course, existential quantification and universal quantification. When we throw those in with a variable in front of a formula, we still have a formula. Now, a formula with no free variables is a sentence. So what is a free variable? A free variable is one that's not in the range of a quantifier. So what I mean by that is, so here's phi of xy. X and y are considered free because there's no quantifiers in which x and y appear. In this one, because x is what we call bound by a quantifier, y is the only one that's considered free. And when they're both under a quantifier, there are no free variables. So the difference between a formula and a sentence is pretty important. What we care a lot about are sentences, formulas with no free variables. So now we can actually start talking about a structures, where we're really getting into like the beginnings of model theory here. Relation. Okay, a structure is a set with a collection of functions, relations, and constants. Let's talk about sets. Now I wasn't actually intending on doing this at first. Lisa, I think you're relatively familiar with set theory, at least like because people were asking, what is a set? How do you define a set? And I was like, we have problems.
Yeah.
when we try to define what a set is. So I was just saying, for now, don't think about it too hard. It's just a bin. It's just a collection of things. And here's the bin containing X, Y, and Z. And we can stack them like Russian dolls.
Yep.
And then some more examples. So I was introducing this notation. This is the relation is contained in, saying more specifically that X is an element of the set. Here's a way of representing the natural numbers.
And set theory as in ZFC, or just like, are you talking within ZFC? Because then I guess the axioms would be helpful, right?
Oh, okay. So I'm just talking about very general set theory outside of ZFC, outside of any axioms. Just what does the notation mean?
Okay. Just within notation, not within any, like, not restricted at all by, okay.
Yeah, no, yeah. So we're just starting. This is set theory is in the language.
Well, I guess is contained in, I was thinking about like okay, yeah, you're good.
Set theory really only has the relation is contained in.
Mm-hmm.
And you can, I guess, define other things with containment. And the empty set, for people who aren't familiar, the empty set is not the same thing as the set containing the empty set. And by empty set, I mean the set, right? The set literally containing nothing, or X, such that X does not equal itself. And this idea of nested empty sets will take us very far. Hint, hint. Remember this for later. Okay, so just a very little bit about sets. So we have some kind of set, an underlying set, like a little universe of objects, like a little universe of the terms and constants. Just a quick, there's a question about this. Functions in relation have fixed arity. So I'm not going to give you some function that takes 3 arguments and then suddenly say, oops, but actually it also sometimes takes 2 arguments.
Mm-hmm.
No, that's not cool. So this here, where we include all of the symbols separately from the structure, is called the language or the signature. It's a way of saying which functions, constants, and relations are we going to be using, are we going to be talking about in our structure. So in this specific example, I'm going to define these are 2 binary functions, A and B are 2 constants, and R is some relation. All of this is syntactic right now. I haven't actually given meaning to what these functions, constants, or relations are doing. And that's because we can have 2 different structures over the same language.
You have a question?
Yes.
Every structure need to have both functions and relations?
Nope.
So the minimum we need is just a function, a constant, and a variable?
No, so here for the language of set theory, all we have is the relation it's contained in. Now you can add other things into your language without problem. Like that's fine, but you don't actually, there's no requirement.
Okay.
Yeah. It's kind of like, I guess you can work with as little as possible, but I mean, if you can throw in extra things, why wouldn't you? Yeah. Doesn't hurt. Okay, so here are 2 structures. Over the same signature. And let me zoom in here and talk about this. So the underlying set, this is how we denote the name of the structure, the set. Here's the F, G, A, B, and R from earlier, except now I've interpreted the elements of my language in my structure. So this is, the integers. And what I've done here, when I've drawn these little Z's on top, is I said, okay, this is multiplication over the integers. And this is multiplication over the natural numbers. And the same thing with the less than relation. So they're slightly different because I've interpreted them into two different structures differently. Now, in this case, they're very, very, very similar. I can come up with, I guess, more examples. I mean, we could just use curly R. Same thing, but over the real numbers. That's not an X. That's supposed to be a times. Cool. So now we have three different structures over the same signature, where all of these were F, G, A, B, and R. Okay. So now we can ask, our sentences, so let's say phi is a sentence, and I'm going to be using this example a lot. Let's say phi is for all x, for all y, there exists a z, x is less than z is less than y. When is this true? I mean, it kind of depends on your domain, right? It kind of depends on what x, y, and z can be. So this is where we talk about how do we discover the relative truth of a statement. So our sentence interpreted in Z is not true, right? I mean, because I can literally have x is equal to 1 and y is equal to 2, and there is no such Z. I guess I could add here x and y and z are distinct. Well, actually, I don't need to because I had...
Because it's not, it's strictly greater than.
Yeah. So.
Wait, I have one more question that I'm harping on, but could you just clarify it again?
Yeah, of course.
What is the difference between a unary function? How do we differentiate a unary function and a relation? And a unary relation?
So an example of a unary function is like the successor function.
Mm-hmm.
So
N plus one.
We'll take in 1 and give out 2,
Mm-hmm.
right?
Mm-hmm.
Whereas a unary relation, Can't I think of a unary relation right now? I guess you could take in some statement, some sentence, and give out 0 or 1, or like false or true for some statement. So in this case, in the function case, we take something from our universe and we get out something from our universe. Whereas for relation, we get the statement of the relation. So there's a difference between like x plus y gives me some other number, whereas x is less than y is just a statement. And it may or may not be true depending on what x and y are.
Okay.
And then if I plug in a specific x and y, I'll get true or false.
And true and false are not part of our language. They're not part of our domain.
Yes. And you're actually getting at like the next thing that I'm going to talk about, which really excites me because it feels like I'm doing something right here. Thank you for being here, Lisa. Thank you for volunteering your time. Okay, so how do we, okay. According to Tarski's undefinability of truth, we definitely cannot define what truth is. So I'm not going to try it. But what I can tell you is when sentences are true in specific structures. So I'm going to define something. I'm going to call this delta. This is where things get really tricky, and this is where I messed up a lot in the last lecture. I think it ended up being more confusing.
Delta is a function.
Kind of.
So I guess how is it what you said in the previous one about the relation? How is it just not a function to 0 and 1?
Because is x less than y, is this true or false?
So can we just draw that to, okay. Okay. I see, okay.
So like,
can we represent it as a function to 0 and 1 instead of true and false?
sure, but it depends on what x and y are, is the thing. Where,
okay, it's not absolutely true. Okay, I see. Okay.
right, it's sometimes true, it's sometimes false, and it depends on whatever parameters like the relation takes, whatever you're supposed to plug in. Whereas the function just gives you the value. It does something to the objects and gives you
a value. It is necessarily true.
It's not even a matter of true. It's like a box, right? It's like a machine that takes in objects, does whatever to them, and gives you another object of the same type.
Oh, okay, of the same type. And then in the relation that you gave, it would be an object of a different type.
Well, the relation itself, I guess you could consider, the relation itself is a formula, right? Whereas the output of a function is a term.
Okay, yeah, okay, that makes sense.
I tripped over myself with this so much the first time I took logic. So like, I'm very, very, very grateful for, wow, my pen is, you know what? Fine, keep the struggle. Whatever.
All right, let's go. Sorry.
Okay, so truth assignment, delta of objects over a structure. So here's curly A. Curly A denotes the structures. Abstract structure, and just capital A is the underlying set. If that seems really terrible to you, that's because it is.
Well, mathematics.
Very, very
thought somewhere on the side that completely changes the whole meaning of everything you just said. Yep.
It's very, very frustrating, especially when it's like, when I was first taking logic, like I naturally write my M's, like my capital M's like that. And then I would be writing, not knowing what was going on. And then I would be like, oh, wait, this one, but then also the closure of that. But it's the algebraic closure of the, oh man.
Yep.
Okay. So please feel free to point out if it's like something is super, if it's like, is that a script A or a curly A? Please ask. Okay. So by objects in A, I mean the set, all the functions, the constants, the relations, and then the terms, atomic formula, and formula. Everything that you can find, everything that you can build up in a structure. Delta is like a function in that it'll take whatever thing that you give it, and it'll give you back an interpretation. So what do I mean? So here's script alpha, and I'm going to give it the two binary functions, the two constants, and the relation. And then again, here's my language. You remember how I was saying we're interpreting these symbols over this structure? We're saying, okay, instead of just two abstract constants, I'm actually going to tell you which constants they are. So we have the structure, and now I can actually start giving you things let's see. So we have delta does different things with different objects. So I'll go through each one carefully. So for terms, so for variables, constants, and then output of functions, delta will take the term. So here's the term x less than y, and here's my structure. Strict inequality. So delta for z takes in the syntactic term x less than y, and what it'll give you is this statement over the integers. It'll do this interpretation. So there's the slight difference. What do I use, n for the other one? So delta takes in the same term from the language, and it'll say this one is over the natural numbers. So these are two different delta assignments. Okay. Variables, all it's saying is now the variables, like when it interprets x and y, all it's saying is x and y can be, in this case, integers, or in this case, natural numbers. Okay. So given an assignment delta, we can now define what happens when I give delta a formula. Well, this was an atomic formula. These are both atomic formulas. So in this case, this is true. If and only if I give you two specific x and y, and I compare them. So like,
does it matter if x and y are free variables or bounded variables?
It matters very much. It matters very, very much. So this is, when we say this is true, we can only decide if an atomic formula is true if either we're plugging in terms. Let's see. Delta gives true or false for formulas under two possible conditions. The first condition is when the term or the formula is when we plug in specific values. Specific terms, which can be evaluated. Or two, when it is evaluating a sentence. When it's evaluating something with no free variables. So here are some definitions. This is an inductive definition, right? I'm spelling out for all of the cases, for all possible formulas. I know this is just like a wall of chicken scratch handwriting. But if you have two formula, then delta of the conjunction of those two is true, if and only if you check the smaller formula and each of those is true. And for the disjunctive case, the delta function says true if and only if at least one of these things is true. Again, for formula, this is only, you only get true or false if you're plugging in specific values or when you're evaluating a sentence. What delta does otherwise is just returns the term formula interpreted in the structure. So there's two routes here. If delta can evaluate something in the structure, it'll tell you if it's true or false. But if it's just something that has free variables, or it's just a term, like 0 in the integers versus 0 in the natural numbers, versus I don't know, if you wanted to have some structure where all of the objects were functions, and then I guess 0 in this new, I'm just going to call it F that I made up. This is like the identity function is a new constant. Delta says, okay, over the integers, we have 0 for the integers. That's not how you write integers, I know. For the natural numbers, 0 for, or how about this? Let's just say empty function. It returns the empty set. And I'll go ahead and define space of unary functions over the category of categories. I don't know, whatever. The set itself, the underlying set itself is a collection of functions, because you can have that. And then delta for this structure will say, okay, my constant is different in this structure. It's different than in other structures. Okay. So here are when delta can tell you a truth value or not. In this case, it's just, it's negation. It's just the opposite. In the quantifier case, it looks a little different. So delta of phi is true if and only if there exists an A in the domain, such that, and this is like a new truth assignment.
Mm-hmm.
So delta of, what this means here is A in the place of X.
Mm-hmm.
When I plug in A, is psi of A true? That's what this delta prime is doing.
Mm-hmm.
And then the same thing for here, except, oof, this is where we really get messy. If I take an object, delta will interpret the object and say, yes, okay, this is 2, the real number, not the integer, it's the real number 2. And then it will plug it into the statement. I need the little delta here, because now I'm taking the interpretation of A, plugging it into the statement.
Mm-hmm.
And then I have to interpret that with delta.
Ow.
Yeah, yes. The important thing here is to realize is this. This is what matters. Delta gives true or false for formulas when you plug in specific terms when you're evaluating sentence. And otherwise, it just gives you the X is less than Y, but delta tells me I know that I'm talking in Z. I know that X and Y have to be integers. Fantastic. We're not really going to be using delta that much at all. The whole point, though, and what I'd really like to drive home is that we have very rigorous definitions for how we break down every single formula. And each term and each structure has a specific interpretation, and we can track everything very carefully. So now that we've gotten here,
are there any other limitations on delta?
Like, sure. I mean, if you gave me the abstract idea of the girl sentence, that the structure literally can't tell true or false,
okay,
then delta, because it is the truth assignment, it can't do anything with that.
Okay, yeah.
It's like going back to this example. For all X, for all Y, there exists Z. X is less than Z is less than Y. Mm-hmm. What you're doing in your head is this true over Z? And you think about it and you say, no, that's delta. Mm-hmm. And
but can we always answer that question?
Only when we're evaluating specific terms and we're evaluating sentences. Mm-hmm. I guess more specifically, sentences that you can actually write down, because you can't write down the Gödel sentence. Because it's like an abstract notion, right? If we could define it, then we'd be able to tell you whether or not it's true. Mm-hmm. So everything that delta does is basically just what you do in your head. We've just formalized it. We've given it syntax, we've given it semantics that are very airtight. Now you can convince yourself, you can rest comfortably tonight that mathematical logic was built with a lot of care in mind. Is this true over R? And delta says, yeah. That's you saying yeah. That's you in your head saying, is this true? You do delta in your head, basically. I mean, you already do in real life. This is just, again, the formalizing. And it's a lot of work, and it's hard to follow. But now...
I guess there's a possibility that I wouldn't be able to do it in my head. So, but delta is set up in a way that it will always give out an output, either that's guaranteed by the way we set up delta.
Oh, yeah.
Other than will terminate is my point. Like, it will...
Yeah, if I have some kind of nonsense, like alternating quantifiers, X plus, and then I have some like ridiculously long formula here, and I'm like, I can't do this in my head. Mm-hmm. Delta can, again, as long as there are no free variables. Wow, my handwriting is really losing it here. Yeah, so it's not like your mental ability.
No. I think that's what I was looking for. As long as there's no free variable, then there will be an output. That makes sense.
Yes, and as long as you can write it down. Okay. Models. Fantastic. A formula phi is valid in a structure under a specific delta assignment. If and only if, when you evaluate it, you get true. And I know that what I've written here isn't clear enough. This is the notation. I'm defining notation here. So this little symbol here is true in the structure. When interpreted under delta. Formula is just plain valid over a structure if for all possible delta assignments. Let's write it this way. True under all delta assignments. Actually, you know what? I shouldn't write this. I should write the script here because this this specifically is different. It's just plain valid if it's valid under any structure. So just plain valid statements.
So this is probably way over the head of this lecture, but it's kind of a silly question, but how would we go about proving that it's valid under any delta that we pick? How would those proofs, what would they have to be?
Oh, actually, so it's not actually over the head. It's like this one. You would say, no matter what I pick X and Y to be, I'll always be able to give you a Z.
For a specific delta though, but not for any delta.
No, actually, those are all the delta.
Because all the variables in that formula are bounded.
Yeah. So again, the only times, so I think you're differentiating between when it's taking in a sentence and when it's plugging in specific terms.
Mm-hmm.
So we plug in specific terms. If every time we plug in the terms X, Z, and Y, or X and Y, we find some Z. Mm-hmm. Or if we plug in X, Y, and Z, and this is always true, mm-hmm. That's the first case. Mm-hmm. The second case is with the quantifiers. So I could say 1 less than 2 less than 3. Mm-hmm. True. So this is the first case. So this is what I mean by under different delta assignments.
Mm-hmm. This is all in the integers. The underlying set is Z, right?
Well, for this part right here, I was just talking about any. I didn't specify the structure, but yeah, I could say this is specifically under the integers. And that would be a good case because this is true in the integers. This is not. Mm-hmm. Okay. Because when we're actually evaluating sentences, we're not actually plugging in specific terms when we're looking at models. We're looking at sentences. We're looking at when sentences are true in a structure or not. We don't have to worry about checking every delta assignment. Mm-hmm. This is just, we're building up what it means to model something. So this is more constructive, mm-hmm. if that makes sense. Mm-hmm. I think that's the best way I would characterize it. Is delta itself is it's a constructive tool that's meant to illuminate, like, okay, these are the methods with which we can do these things very rigorously, but we're not going to be using delta. I mean, I think Julia once mentioned that eventually you can mess with delta assignments when you do forcing, but honestly, that sounds like a whole like chirp on mushrooms, and I can't go there right now. Okay. A formula is satisfiable if and only if there exists a structure and there exists a delta such that under that delta assignment, the formula is true. So here's an example that's not a sentence. X is less than Y and Y is less than X. Here's a formula. All free variables. All variables are free. Is there a model? Is there a delta such that this is true? And the answer is no. Right? Like, we know it's not possible for something to be strictly less than something and strictly greater than something at the same time. I said that backwards than the things that I underlined, but we're just going to move on from that.
Yeah.
So this is how we can say a formula, not a sentence, a formula is not satisfiable. It's inherently contradictory.
Mm-hmm.
Such a thing is not possible.
So is there a middle ground example where it's valid for some but not all deltas?
Yeah, actually that would be back up here. For this, there's one delta assignment that'll say, I'm going to give these values 1, 2, and 3, and that's true. There's a second delta assignment that's going to ask the same thing for 2, and there is no such thing.
Mm-hmm.
But satisfiability is different. It's if there exists any delta. And so here's an example. Like, if I wanted to say this differently, I could say, this is the same as saying, there exist parameters such that when I plug them into phi, A models phi. And I should make it clear that the xn are in A. So if there exists a way to satisfy a formula, then the formula is satisfiable. We really only care right now, at least for with things that are satisfiable. We don't care about any case like this.
Mm-hmm.
Because what good is that going to do us, right?
Mm-hmm.
And then we can talk about when theories are satisfiable. So a theory is just a collection of sentences. And I think, Lisa, you asked specifically for some algebraic examples. So because I have about 9 minutes left, here's the theory of groups. Let's see. The language, let's just say star for some group operation. We need some unary function that gives us the inverse. We need some constant, which will be the identity. So here's the language. I might be forgetting something. It'd be really embarrassing if I messed up the theory of groups. So for all x, there exists a y. X star y is equal to e. Well, I'm sorry. X prime. And then I'm going to say these are inverses of each other. Boy, that's a really bad idea notation-wise. For all x, star e equals x. Associativity. Great. Cool. Here's the theory of groups. I've written down 3 sentences with all of which have no free variables. And now I can ask, what are the models of the theory of groups? Groups. Groups are the models for the theory of groups. Anytime you come up with a group, and it's a structure. every time you come up with a group, you're coming up with a structure that models the theory of groups.
Mm-hmm.
I mean, that's how you've defined it. I got really excited when I learned this because it finally made the difference between a language and a structure and a model actually makes sense.
Mm.
Like I was finally able to understand what the heck I'd been doing all semester.
So how can model theory tell us new things about groups that we wouldn't have been able to do through just doing algebra? Like how is netting it out to, what can we say about the theory of groups from learning model theory and from understanding the delta?
Holy cannoli. Well, what we can do is let's write this. We can compare the theory of groups with the theory of abelian groups,
Mm-hmm.
with the theory of rings, with theory.
When you say compare, I guess, what do you mean?
So theory of groups, these three axioms,
Mm-hmm.
right? So I am going to label it like this. So it's, I think, pretty clear that the theory of groups is contained in the theory of abelian groups.
Mm-hmm.
Because for abelian groups, all we need to do is we just need to add another sentence.
Mm-hmm.
So I can mean compare in that way. And then there's a lot of different ways to actually compare different theories.
When you say contain, you mean the axioms? Like, I guess in that sense, you just look at the axioms of all the theorems and see which ones, so which contain which. So it's really a relation between the axioms.
Well, there's much more than that. I'm trying to give.
For sure. Sorry, that's fair.
Yeah, no, I'm trying to give a concrete example.
Yeah, that makes sense.
So here's like the axioms for the theory of group, I guess the sentences, and the theory of, as I could say, the theory of groups, union stuff commutes.
Yeah.
But then beyond that, now I can actually build
union more stuff and then get other stuff. Yeah.
Right. So what you see in model theory, I think that is so, so, so crazy is it's like, given a model of some theory, the theory is complete, decidable, show that M also models the theory, union this statement.
Huh.
And you have to be able to prove that. Where this statement is something like, there are no finite objects in my universe. Every object in my universe is infinite. Mm-hmm. And then it's like, how do you build a model?
How do you show that's really cool? Like, how would that prove that's really cool? How do you show that proof that you can union that truth with something else and still have it be complete and decidable?
So I just threw this out there.
That's okay.
I remember I think it was my first exercise sheet that I did in 225A was something about models where every object is infinite. Mm-hmm. And you had a theory and you were unioning that statement. It was like, show that this theory is satisfiable. Oh, which brings us back to satisfiability of a theory. A theory is satisfiable if and only if there does exist a model. And to be clear, it's a model of each of the sentences. The same structure models them all. It's not like, I have this one models the first one, and I have this one models the second one, yada, yada, yada. That's not cool. We mean the same one. Mm-hmm. So I think really quickly before I end this talk, because I actually have to call somebody in a few minutes, it looks like we covered everything. I think that as far as the confusion with the delta assignments goes, this is the money. This is the important thing. It's the interpretation. It interprets things in the structure. That's just take that away from this whole hour. If you've listened to the whole thing, just take that away from here. And then as we talk more about model theory, which is, oh man, model theory has like kicked my ass time and time and time again on the numerous exams that I've taken and the numerous homeworks I've tried to do. I'm always like, oh God, but the thing that's so cool is the models for the theory of groups are groups. And what we're talking about when we're talking about theories of structures is we're abstracting the structures into their literal, the finest requirements. And it really reminds me of Plato's allegory of the cave.
Mm-hmm. I like that a lot.
Yes, so like every group is a shadow.
Yep. Yeah.
It's the same form, and this is how we learn. This is how model theory teaches us so much about the structures, because instead of talking about the actual things just inside the structure, we're talking about how it relates to other structures, as well as what do we literally require? What does this all completely boil down to?
Mm-hmm.
And there you have it. That's my take on the very beginnings of model theory.
The very beginnings.
Oh yeah.
TBD.
That's the stuff. This is the stuff that like honestly gets me up in the morning, is thinking about like, oh my God, I have to take these exams. And my watch always goes like, your heart rate is above 120, but you've been sitting still. And I'm like, yes, I know I'm in a model theory exam right now. It always kills me, but when we get back to it, it's really, really interesting stuff. So I'm really excited to go more into model theory in the coming lectures. So everybody, thank you so much for listening.